I'm not saying that this meter is better than a Fluke. I just compared it to the industry standard to show how decent it is. Basically, when I was looking for a meter I was thinking about putting up some electronics teaching videos. So I was looking for a meter that would be affordable for someone who's just deciding whether they want to get into the hobby or not. You're not going to take this and go out and work on a 480 volt system. It's just not going to happen. It's just a bench meter to learn electronics. That's it, period. It's not to replace a Fluke 87. Fluke 87 is what it is. It's an industry standard. I'm just comparing this to this. This is kind of like, if a parent were going to have their kid take guitar lessons, they're not going to go out and buy a Stratocaster. They're going to buy probably a Squier or some other instrument so that if the kid loses interest, they don't lose any money. That's what this is. This is just a meter that has a lot of functions. It has a signal generator and an oscilloscope, so you can see what's going on in electronic circuits. That's all. Not replacing this, okay? It is what it is. I mean, I've had a lot of comments like, I would never use that. Look, it's an inexpensive meter. That's all. So let's get on with the capacitance checks that I screwed up last time, and I apologize for that. So in my last video, I made a mistake, and yes, the Fluke 87 can do capacitance. Basically, what you have to do, and I forgot about this, was go to the ohms reading and hit the yellow button, and then it'll do capacitance. So we're going to do 4 capacitors, write down the readings we get, and then compare them to the 2C53T again. So the first cap, we got 78.6 nanofarads. The second cap, we got 10.87 nanofarads. The third cap, we have 0.535 microfarads. And the big cap, we get 1026 microfarads. So we're going to compare the results of the Fluke 87 to the 2C53T. So in the first cap we get 73 point, and now it's saying 72, 72.75 nanofarads. On the second cap, we get 10.65 nanofarads. On the third cap, we get pretty close to the Fluke, 535.6 nanofarads. And on the last cap, 1.012 microfarads. So if we take a look at our results, and this is the one that was messed up, but it was 72.75. So we got 78.76, 72.75, 10.87, 10.65, 0.535. Same thing in here. If we move the decimal, we've got 0.535, so pretty much dead on. And the big one was 1,000 microfarads, 1026 to 10112. So you can see they're relatively close. Who knows which one is closer? But just for general purpose, the 2C53T works. And like I said, I love my Fluke. I'm not going to do away with it, but the difference in price is $100 versus $400. So if you're just starting out, again, this is not a bad piece of test equipment. So let's talk about capacitors in general. We know that this cap is marked 1000 microfarads, and that is the minimum that you should get. If the meter reads over that, it doesn't mean the cap is bad. It just means the manufacturer gave you a better product. Now, just because the microfarads read right, that doesn't mean this cap is good. The only problem with both these meters is that neither one of them can read ESR. They're not set up to read equivalent series resistance. So there are 3 checks that you need to do to a capacitor for it to be good. 1, you need capacitance. So we can see that both these meters made this cap good for capacitance. 2, ESR, equivalent series resistance. And that is the resistance within the cap if it goes too high when the ESR goes bad. Usually the capacitance will read wrong, but you really need ESR. So what is ESR? It's equivalent series resistance. So what we're doing with an ESR meter is we're actually trying to find Z, impedance. We want to know if this cap acts like a resistor when we want it to act like a filter. So we want lowest ESR value. So basically what you're doing is calculating Z of the cap, which is 1 over 2 pi FC. That's your formula right there. So it's trying to figure out the impedance of this cap. So most ESR testers will put 125 kilohertz across a cap and then try and figure out what Z is by this formula. And if that's too high, in essence, you want an electrolytic cap to be 0 impedance to any frequency because you want them to filter it out. So that's what you're figuring out. So this is a dedicated ESR meter, and we're going to hook it up. And we see that we're reading 0.07, 0.07 is where it hung up. So let's call the ESR of this cap 0.07. So at 1000 microfarads, and this is 1000 microfarads at 50 volts. So if we go on the chart, 50 volts, 1000 microfarads, this is saying 0.06 should be your minimum. But at 0.07, I'm not going to, it's close. It's real close. I would still call this cap good. So this is the table that was pulled down from a Sencor cap tester manual. This is from an LC102 manual. Sencor made some nice cap testers. You know, some people call them junk, but they actually work pretty good. We had an LC75 that I really liked. They make an LC102 and they make an LC103. And on our cap, we can go to 1000 microfarads and come over here to 50 volts. So 1000 microfarads, 50 volts. We can see that our ESR is allowable at 0.332. So we had 0.07, so that's good. So the third thing we have to check is leakage, and that is the amount of current that'll flow through the cap. And the cap would be acting like a resistor in a quiescent state. So The following is how we do that. So what we have set up on the bench is a test setup to check capacitor leakage. We have a power supply here, which is going to supply a variable voltage from 0 to 50 volts. We have a current limiting resistor of 2.7 kilo ohms, or 2700 ohms. Our meter, our positive lead, is set to the ammeter function. Positive lead is set to the positive part of the voltage. The negative goes to the capacitor, so we can read series milliamps through the circuit. And here's our 50 volt 1000 microfarad capacitor. So what we do is we bring this voltage up very slowly, because the meter is 1 amp max. So we don't want to go over 1 amp max, otherwise we'll blow the fuse. Right now I'm sitting at 16 volts and I have 0 milliamps. So you can see when I increase it, I'm up to 17. It's going to increase while the capacitor charges and go down to 0. We have to bring this up real slow, not exceeding 1 amp. All right, right now I'm at 25 volts, and you can see the meter going down. And we're going to go all the way up to the 50 volts. Okay, so we'll check the voltage across the cap, or the voltage across the circuit. And you can see with my hand out of the way, we do have 50 volts DC. You can also see that our milliamps is counting down. Right now we're at about 270 microamps, or 0.026 milliamps. We're going to let that go. So we know that we have 50 volts right here. And down here we can see that we have 1000 microfarads. So if we come across the 1000 microfarad to the 50 volts, and it's kind of hard to see, but it's grayed out, but 1342 microamps, okay? So if we move the decimal point over 3 places, we have 1.342 milliamps. So right now, we're at 15, but we're slowly going down. So right now you can see we're down to about 3 microamps, 4 microamps. I would call this capacitor good. It's not drawn. If you have a bad capacitor, it's going to be drawing pretty hefty milliamps. So since this thing passed ESR and it passed everything else, I would say as you're building up the oxide coating, this number is going to go down. That is basically how you would check leakage with just a resistor and a meter. So now what we're going to do is turn our voltage off. But what we're going to do is disconnect the meter at this point. And this is a capacitor shorting device. We want to take all the voltage off that capacitor. There's still voltage on there until you discharge it. So what we're going to do here is discharge it the rest of the way. And this is how I built my discharge unit. I got a 47 ohm 2 watt resistor in there. And people say, well, yeah, you could fry that. Well, it's instantaneous voltage and it seems to dissipate rather quickly. So this works really good for me. I don't generally work on stuff that's real high voltage, 50 volts, 100 volts, it'll get that. Then across the side of it is a diode, and I believe this resistor is about a 5.6K. So the 47X is a shunt. You get the light just for a brief second as the voltage is high enough to light the LED, and then once it's gone, the cap is just discharged. The nice thing about these probes that come with this meter is they're small enough to stick right into your working board, which is unusual because most meters are a lot bigger than that. Now, it doesn't mean that they'll be, you have to be careful because they probably break off rather easily, but the fact that you can stick them into a board like that is nice. So that's the only way you know that a cap is good. It passes all three of those checks. A lot of people, a lot of amp repairers and people in repair, just because a cap is old, they replace it. And that may or may not be good because a lot of times you can pull a cap off the shelf and that cap will test worse than the cap that you have in the equipment. So it's kind of a personal call on whether you should replace it or not. But if the one in the unit tests better than the one that you get as a replacement, for me, I'd leave it in there, even if it is 20 years old. I've had 20-year-old caps that looked like they were leaking, and they actually checked far better. And what happens, a lot of times in these electrolytic caps, there's a fluid. There's an electrolyte in there. So if this cap sits on a shelf, there's two plates. You have a positive and a negative plate, and then you have the electrolytic component and probably a piece of paper or some kind of insulation in between that. But what happens is the electrolytic fluid eats into the oxide coating. When you put voltage on this, it creates an oxide coating, an aluminum oxide coating on both plates. And as those plates build up, your capacitance gets better and your ability to filter stuff and everything like that gets better. But if it sits on the shelf, the electrolyte eats into those two plates. So when it eats into those two plates, if you don't form the capacitor, and forming is just a matter of putting a voltage on it, like 1 volt at a time, and slowly moving it up and letting it sit on voltage for a time to build up that aluminum oxide coating. Because if you don't do that, you can put a brand new cap in a piece of equipment and it'll fail really fast with infant mortality. So it's always a good idea to form your caps before putting them in there. People say, oh, that's BS. And it's like, well, it's not, because you're creating that oxide coating on this thing and making it better. And that's why a lot of caps that have been in the equipment, if they've been used, their oxide coating is perfect, even after 20 years. So in conclusion, I apologize for the mistake on the other video, but it gave me an opportunity to go in and explain capacitance much further. So thanks for watching. Please like and subscribe, and we'll see you on the next one.